All right, so this is Jonathan Knobloch presenting on behalf of David Amanze for our project Multi-Label Classification CNNs based framework to detect chest X-ray abnormalities. So what exactly we're doing is we are using deep learning techniques in correlation with object detection techniques on a data set of chest X-ray images. We are then building a machine learning algorithm designed to detect diseases based on a chest X-ray input. So for our machine learning, we are using a TensorFlow backend with a Keras frontend, and we include the version that we're using on the bottom of the screen there in case you're curious. The dataset we're going to be using for this project is going to be the Chexpert chest X-ray dataset. It contains over 200,000 chest X-ray images from over 65,000 unique patients. It was released in February 2019 by the Stanford Machine Learning Group and is also currently a competition for the highest score. So this dataset contains 14 different diseases, with the 14th being a no-finding class. Our approach can be broken down into 3 stages of training. So for the first stage, we're going to pre-process all of our data. In the second stage, we're going to use conditional training to learn data hierarchies and dependencies. And then in our third stage and final stage, we are going to complete our training by running the full model. Alright, so for our first stage of pre-processing, this is the stage where we're going to aim to remove some of the bad sample from this dataset. So these large chest X-ray datasets often feature a huge number of chest X-rays, and they're not always combed through perfectly. And they often result in having a lot of bad sample within the data. So we set up a template matching algorithm to match a template of a chest X-ray to what we see within our data. And then if it doesn't match the threshold for what we're looking for the matching, then we remove it from our data. So we ended up removing about 20,000 images from the data set, leaving us with around 200,000 remaining. If we look here, we can see the template that we used for both our frontal and lateral X-rays, as well as some of the examples of bad X-rays that were removed from the dataset. Alright, so for the next stage of our training, we're going to move on to the conditional training. This is where we're going to learn the data hierarchies that exist within our data. So if we look at the figure on the right, this is the data hierarchy that is presented from Chexpert from the Stanford Machine Learning Group. This is the hierarchy we expect to see within the data. But when we actually go within the data, there are cases where diseases such as edema, which shouldn't be able to be a positive unless its parent, lung opacity, is also positive. Within the data, we'll actually see edema being positive without lung opacity being positive. And this is a discrepancy that isn't represented within this hierarchy, and it kind of throws doubt onto this hierarchy and provides a little bit of a path of you can kind of create your own hierarchy based off of what is within the data versus what is supposed to be represented within the data. So because of this, we are able to have a couple different ways that we can train our model. We can use slightly different hierarchies. We can either train based off of what is within the data or what we have been presented from Stanford. And we can also go little stages in between to tweak and get more accurate results for specific diseases. So for our final training stage, let's go ahead and describe our model that we're using. So after the conditional training, we freeze the upper layers of DenseNet 121, and then we re-implement those into our full train that will be going across the full data set. We're using the Atom Optimizer with default parameters, batch size of 16, and the default learning rate, which is set to 1e to the negative fourth and reduced by a factor of 10 for each epoch. You can see our loss function here at the bottom. This is the same implementation that we learned from the current leaders of the Chexpert competition, and they have confirmed that DenseNet is the best working transfer learning for this dataset, so we're using their implementation in these regards. We also are implementing our own label smoothing technique. So there is an uncertainty label within this data set. There's a 1 for being positive for the disease, 0 for being negative, and -1 for uncertainty. So we are using a label smoothing technique that is a predicted value based on our trained model. So our trained model runs back through and predicts for the uncertainty values. We get a prediction between 0 and 1, and then we scale that between 0.3 and 0.7 to get a kind of random number with a little bit of weight to it to help our training. So if we look at our results, these scores we see are the area under curve here, and we are focusing on these 5 diseases because these are the 5 diseases that are focused in the Chexpert competition. So as you look through these trainings, our first training is based on a data hierarchy that is represented within the data. The second train is based on the hierarchy that is released with the data set, and the third and fourth trains are both based on hierarchies that are loosely based on the hierarchy that was released with the dataset, but slightly tweaked. So you can see how the results greatly shift between these different hierarchies, and how different hierarchies can lead to specific results that you can tweak based upon the needs that you are looking for in your model. So for the conclusion of this, our conclusion is just generally that conditional training and label smoothing play a huge role in changing the types of results that you can expect from your model, and that if a data hierarchy is open for interpretation, like it is in this project, experimentation is always going to be the best way that you can find ways to address your model specifically for the needs that you're trying to get out of it. All right, we'll be available for a Q&A after this in our Zoom meeting. Here are references for this project as well. We hope to see y'all there.